with a metal chain. Here we are demonstrating the operation of a retarder, a mechanical retarder, which can be used for electric cars, as well as other vehicles with internal combustion engines. To visualize the process, we have installed plexiglass here. Here on one axis, we have a row of bearings inside which are distributed a segmental disc or with elastic elements. In this case, the elastic element is located along this axis. So when we apply pressure here, we create it in the caliper, and pressing occurs, these bearings move against each other, thereby creating an opposing torque. This retarder can be used along with recuperation for electric vehicles very successfully. It is lightweight, and we will make it even lighter. Let's start by showing it without the motor turned on. Please, Norman, show us how the retarder itself works. All right, I am going to go ahead and turn it on for you right now. Okay, turning it on. Show it here. Okay, press it again. Hold it like that, hold it. So the bearings move in opposite directions, and from both sides, the calipers, or rather the caliper cylinders, create movement which deforms the elastic elements and expands them. Okay, press it again. Okay, you can see these guides. They are positioned within the guides and move in opposite directions. Okay, that's enough. Now, Norman, please turn on the motor. We will show it in operation now, how it creates the opposing torque, the braking torque, how it creates it. Turn it on, please. It's not electric, not hydrodynamic, it's a mechanical retarder that works in almost any environment. It doesn't heat up at all. At most, when it's been running for 2 hours, it might heat up in continuous operation. It might heat up to about 60, 70 degrees. It doesn't heat up any more than that. In this case, the power it overcomes brakes. Please show the motor down here, 17 kilowatts. It has, two pulleys that are positioned 1 to 2. It turns out to be 3-4 kilowatts. It can stop about 40 horsepower. For electric cars, for passenger cars, this is very convenient. It will unload, it will not wear out. Wear out, I mean the braking system, the main braking system of the wheelbase, right? It will thereby serve for a long time. It will determine the durability of the wheelbase. Besides that, we could use it in the wheelbase. We can use it directly for, well, in this case, we did it for a Mercedes. This has already been shown earlier. It can be used for the wheelbase, but even in this case, it can also be used in parallel. Its advantage is that it doesn't heat up, it doesn't overheat, it doesn't operate in any environments, and it doesn't require any additional, let's say, reconstructions and so on. It integrates well into electric vehicles, and it integrates well into internal combustion engine vehicles because it is lightweight. If you pay attention, the size ratio is shown there in the picture. We were making a lighter retarder. For example, this is an electrodynamic retarder that is used for trucks and so on. And here is our retarder, which can be used. If, for example, with this electro retarder, when we transmit current, it is absolutely necessary for full efficiency to supply a current of 200 amperes per hour, and it reaches 600 degrees Celsius at maximum load. At maximum load, our RSS-Hook retarder's temperature only rises by 60 degrees. There. The same comparison was already carried out in detail by us. So the use of, let's say, Foucault currents, as well as the use of electrohydrodynamic ones and so on. Compared to all of them, our retarder is better in all characteristics because it does not use weak Foucault currents, which under a heavy load of 200 amperes per hour produce high temperatures, or let's say even weaker is the hydrodynamic retarder, which also heats up. And most importantly, none of them work at low RPMs. Here on the graph it shows how different retarders, well, as the shaft rotation speed decreases, their efficiency immediately drops, the torque drops. With our retarder, the torque doesn't drop at all here. It can operate, therefore, at low RPMs. And what's remarkable is that if you look at electric recuperation, we know that even electric recuperation works very poorly at low temperatures. Since there are no chemical elements involved in braking here, like batteries, for example, there's no chemistry here at all, it can operate even at low temperatures. And furthermore, when your battery charge is at 90–100%, that's the highest level. In that state, the recuperator doesn't work. Ours does work. It can serve as a good platform for scaling the braking characteristics of an electric vehicle alongside regenerative braking. That's all.